Hello everyone, welcome back. So let us start. We'll first quickly recall in the last class what are the things we had covered. I defined what is homomorphic encryption. That means suppose this is my plain text and this is the operation it is having star, and in the case of ciphertext it is say dot. Then if you want to encrypt on the plain text E star B, then this will be encryption of E dot encryption of B. In the case of addition, it will be encryption of A plus B. It is encryption of A plus encryption of B. In the case of multiplication, this. So I told you some the types: partial homomorphic encryption. It it can solve only one type of gate, either addition or multiplication. And I gave you example RSA, Goldwasser-Mikali, Paillier, ElGamal, and BGN. Actually, we'll talk about BGN. It's not under the partial. Actually, it can perform both. I'll just put it a box. Focus on that. Today's last topic will be BGN. So today I will be covering ElGamal. In the last class, I had covered RSA and Goldwasser-Mikali. Today we'll be covering ElGamal, Paillier, and BGN. And what is somewhat homomorphic encryption? As I told you, you can evaluate two type of gate, but only for a subset of circuit. In the case of leveled homomorphic, two type of gate of bounded depth. As I told you, what is bounded depth? For example, suppose I am saying degree phi, so all the polynomial of degree phi can be solved. This was the example. And what is the fully homomorphic encryption? You can do any type of gate, multiplication, addition, or anything of unbounded depth. Give me any circuit I can solve with this. This is what FHE is. And then we give you RSA, that is unpadded RSA, because there are one more form of RSA. I am taking unpadded. Okay, in that case we saw that it is homomorphic with respect to multiplication. And what about Goldwasser-Mikali? We saw that this is homomorphic with respect to addition. And yes, now let us come back to the third one, that is ElGamal. This was given in 1985. Okay. Now ElGamal, it is based on discrete logarithm problem. That is suppose A is the secret, and say you are given with say k equal to g raised to a. Okay, the question is that given g and k, can you get the value of a? This is the question. This is your discrete logarithm problem, and it is hard to get this in the case of modulo n. In the case of modulo, it is a hard problem. Otherwise, you can simply get it. It is the log of k with the base g, correct? But in the case of modulo, you cannot apply this part. That's why it is a hard problem. Okay, now let us start. What is the key generation, encryption, decryption? First, in the case of key generation, we'll change the color. First of all, choose a large prime P and then construct a group ZP star, okay, multiplicity group, and use a primitive root G modulo P. So G is your primitive root, and also take a random number from 2 to P minus 2. Okay, so what are the things I have taken now? I have taken P, I have taken a G, and I have taken a E. Okay, and calculate this capital E. Capital E is what? G raised to A modulo P. And now let us see what is public key. Your public key is going to be P G and this capital A. And what is your secret key? Secret key is small a, this guy. This is your secret key. Another guy are public key. This is P, G and A. Okay, now let us see how do you encrypt. For the encryption, as by the definition we have to use only public key. So in the case of encryption, suppose there is a message M which belongs to ZP star and I would like to encrypt it. So choose a random number, choose R which belongs to 2 3 random number. I am writing R here, 2 3 up to P minus 2, and calculate this. Calculate C1 which is equal to G raised to R modulo P. Okay, this R whatever you have chosen here, and calculate C2 which is M into E raised to R. Now if you observe something, we are actually masking our message. This is my message, I am putting a mask here. This is E raised to R. You cannot, by looking at C2, you cannot get the value of M, your message. And now this is the encryption. So what is your ciphertext? It is C1 comma C2. So do you observe your ciphertext size is double now? Your message, this is double of your plain text size. Now let us see in the case of decryption. In the case of decryption, you calculate first a key. What is this key? That is C1 raised to A modulo P, and then the message can be calculated as M equal to K inverse C2 modulo P. And if you check the decryption, if you check the correctness, it is very easy. You just see what is K. Let me find this. K inverse C2. Now what is K? It is C1 raised to A, and what is your C2? It is M into A raised to R modulo P. What else? Now we know that what is your C1? C1 is G raised to R, so it is G raised to R. It will be G raised to AR. Okay. Oh wow, am I doing any mistake here? This is K inverse, so it will be C1 raised to minus A, so it will be minus A. Okay, multiplied by M multiplied by E raised to R. What is your A? Yeah, the value of A here. Do you see where it is? G raised to A. It is G raised to A. So it is G raised to A raised to R. So it will be G raised to AR modulo P, which is same as M. So correctness was very easy. So this was the crypto system here. Okay. Now let us again check whether it is it is homomorphic, it is satisfying or not. Okay. Suppose I'm having two message 1, message 2, and the ciphertext for this message I'm writing it as say C11 C12. So I'll just write C11 C12. What is the value of C11? Yes, it was G raised to, I'll say G raised to R1. Okay, and what is the value of C2? It will be M1 multiplied by A raised to R1. Okay, and what is your A? Yes, it is G raised to A. This A is same for both. Okay, and here what about this? I'll write it as C21 C22. So in this case it is G raised to R2 and M2 into E raised to R2. Okay, now let us see what about addition. Whether if I add these two ciphertexts, this is your C1 ciphertext, this is your C2 ciphertext. If you add these two, what happens? C1 plus C2, it will be coordinate wise addition. And if you observe, the first term will be g raised to r1 plus g raised to r2. So it clearly tells that it is of no use, because this cannot be written as something g raised to something, g raised to some r. Correct? So it is of no use to us. Is it clear? Yeah. So, sorry. Why this is happening? Yeah. So I'll put a cross here because addition is not satisfying in our case. Okay. Now what about multiplication? Multiplication here, C1 into C2, that means coordinate wise multiplication I am talking about. C11, C12 multiplied with C21, C22, which is equal to C11 into C21, comma C12 into C22. Now let us see what is the value. What is C11? It is g raised to r1, g raised to r2 multiplied with m1 into e raised to r1 into m2 raised into a raised to r2. What do you observe? Now it is very simple. This can be written as g raised to r1 plus r2. Okay, and here this can be written as m1 into m2 multiplied with e raised to r1 r2. Sorry, r1 plus r2, which can further be written as this. I'll write g raised to r. This r is equal to r1 plus r2, and this is m1 into m2 e raised to r. What do you observe? This is actually encryption of m1 into m2. So this ElGamal is homomorphic with respect to multiplication, not with respect to addition. So again, this is again a partial homomorphic encryption. Partial homomorphic encryption with respect to multiplication. Only one gate. Okay. Yeah. Let us go to the next part. Next is your Paillier crypto system. Paillier crypto system. Encryption scheme, whatever you say. And now the year is 1999. Okay. Yeah. Let us see what is. We'll quickly go. Let us see what is key generation. It is also based on your integer factorization. Okay. Choose two large prime numbers. Say P and Q. I am choosing two large prime number independently to each other. And one more thing, GCD of your PQ, comma phi of P, or rather say P minus 1, Q minus 1. That is 1. Okay. This property assures that both have the same length P and Q. And now compute N, which is P into Q, and calculate lambda, which is LCM, least common multiple of this P minus 1 and Q minus 1. Okay. What else? Select a random number G, randomly select from Zn star, Zn square star, multiplicity group over n square. Okay. Now here one thing you have to make sure. Okay. Ensure that n divides the order of G. See, G belongs to Z and n square star, correct? So ensure that n divides order of g. How can you ensure? Again easy, by checking the following multiplicative inverse. By checking the existence of mu. Suppose mu is equal to the L of g raised to lambda and modulo n square. Okay, first bracket, second bracket, and then third bracket, inverse modulo n. This is your mu equal to inverse of this. If this mu exists, then you can ensure that this n divides order of g. Okay, what is this L? This L of u is defined as u minus 1 upon n. Okay. See, division is possible because here E by B, that means E into B inverse. So B inverse should be there in modulo n. Okay. Now let us see what is public key. Your public key is n comma g. And your private key, secret key is lambda comma mu. Let me just quickly show you everything once again. What we did, we started with 2 prime, and then we find out what is n equal to pq, and then lambda, then this, and choose a g such that and divides the order of g by checking this condition. Okay, and the public key is n comma g. Public key, this is n, this is g, your public key. And what is your secret key? Where is that lambda? This lambda is your secret key, and mu, these two people are your secret key. Now let us try to encrypt. Okay, now before encryption, see what are the things we had done. We could have taken other parameters, just we have to make sure that your g is equal to n plus 1, lambda equal to pi, or I'll just write, maybe that may help you. If P and Q of equivalent length, a simpler variant of the above key generation. Key generation steps would be to set first g, that is your n plus 1, lambda, that is phi of n, and mu equal to phi of n inverse modulo n. Okay, yes, and phi of n you can easily calculate, p minus 1 q minus 1. Yeah, so just because we were not sure whether p and q are of equivalent length, so we did that. Otherwise, if p and q are equivalent length, then we could have done this: g equal to n plus 1, lambda equal to phi n, mu equal to phi n inverse. Okay, now see the encryption. Okay, now suppose I am having m which is in Zn. I would like to encrypt it. Okay, select R, which belongs to Zn star. Okay, compute the ciphertext. Your C will be G raised to M R raised to N modulo N square. This is what your C is. G raised to M R raised to N modulo N square. What is the decryption? Will you do the decryption? In the case of decryption, the C you are having here, compute this. Your plain text can be computed by solving L of C raised to lambda modulo N square multiplied by mu modulo N. You just have to multiply these two things, you'll get your plain text. Okay, if you observe, what was your secret key? Secret key was lambda and mu, so I'm using this lambda here in the keys in the decryption. Okay, if you want to see the correctness is very easy. You just have to observe one thing. Yeah, let us see the correctness now. What is this lambda? What is the value of this? L of C raised to lambda modulo N square. So let us see C raised to lambda. I'll change the color so that easily. C raised to lambda. Let us see. What is your C here? G raised to M R raised to N. Okay. This is C raised to lambda and modulo N square. I would like to calculate this. Now let us see L of, what was the formula for L of, what was the value of L of U? It is U minus 1. L of, say X, it is X minus 1 upon N. This was the definition. I would like to find L of C raised to lambda, which is equal to modulo N square. Don't forget that. Modulo N square. The value will be X minus 1. So it will be G raised to M R raised to N minus 1 divided by N square. Okay, yes, this is what you are having. Now what is your value of mu? If you observe, mu is phi n inverse. And what is the value of lambda? I wanted to calculate C raised to lambda. I just put raised to lambda. What is lambda? Phi of n. So this is raised to phi of n. Okay. Yeah. What is the value of phi of n? Yeah, so I think I made a mistake here. The definition was L of x equal to x minus 1 by n. Okay, so just erase this part. Yeah, let us see. I'll try to see this. L of C raised to lambda modulo n square multiplied by mu, that is what our aim is to check. Now what do you see? L of, no, let us not solve. What is the value of C? It is G raised to M R raised to N phi of N. So it is G raised to M and R raised to N. So I'll write M into phi of N multiplied by R raised to N into phi of N modulo N square. Now if you see modulo N square, what is phi of N? It will be, so this part will be gone. This is actually 1. This is your phi of N square, N into phi of N. This is 1, so I'll be having what? I'll having Z raised to M phi of N modulo N square. Okay, now one more thing, observe that multiplied by mu. What is mu actually? Mu is your lambda inverse multiplied by, and what is your lambda inverse? What is your lambda? Lambda is equal to on the top I was having lambda and I wrote 5 in here. Oh, and this is lambda. This is lambda. The value of lambda is actually that, so that is not an issue. I'll just write lambda. So this is G raised to M lambda multiplied by R raised to N lambda. And if you observe, what was your lambda? P minus 1, Q minus 1, LCM actually. Okay. See, lambda is phi of N, yes. So now observe that this is G raised to M lambda modulo N square multiplied by lambda inverse. This is what you are having. Now let us apply. What is the formula for L of x? X minus 1. So it is G raised to M lambda minus 1, and actually this is modulo G raised to M lambda modulo N square, or I will just write it. Lambda minus 1 modulo N square C divided by N, or having multiplied by lambda N. Okay, now observe one thing carefully here. Your G was N plus 1, so this is N plus 1 raised to M lambda minus 1 modulo N square multiplied by N into lambda inverse. But do you see, if you see with the binomial expansion, it will be 1 plus M lambda plus other term will involve M lambda and other term will be N square. So it will be 1 minus 1 divided by N, which is 1 and minus 1 will get cancelled. I'll be getting M lambda, and outside I was having lambda inverse, so I'll be getting my message M. So this was the correctness we have checked. You know, one thing you have to observe here, that I wrote G is equal to N plus 1. So to use this binomial expansion part. Okay. Yeah, now let us see. Encryption, decryption, everything is done. Now let us see whether it is homomorphic or not. So I am having to gain 2 messages, say M1 and M2. And what was the encryption here? If you remember, we have to choose random R. So I'll choose random R1, say belongs to Zn star, and here R2, which belongs to Zn star. Okay. Now what is the ciphertext? C1 equal to G raised to M R raised to N. So M1 R1 raised to N modulo N square. This is your ciphertext C1, and here your C2 equal to G raised to M2 R2 raised to N modulo N square. This is what you're having, C1 and C2. Now, suppose I'm adding 2, C1 plus C2. Am I getting something? I'll be having G raised to M1 R1 raised to N plus G raised to M2 to R2 raised to N. Can I write it as some G raised to something and R raised to something? Yes, there is nothing common actually. So I cannot. Again our box and then cross. Addition is not possible here. Yes. What about multiplication? If I try to multiply this C1 and C2, I'm having G raised to M1 R1 raised to N multiplied with G raised to M2 R2 raised to N modulo N square, which is equal to G raised to M1 plus M2 multiplied with R1 R2 raised to N modulo N square. Is that clear? So if you observe, this is actually of the form. This is the encryption of M1 plus M2. This R1 R2 can be written as R. Okay, this is the encryption of M1 M2. So it is again partial homomorphic encryption with respect to addition. Okay, to quickly summarize, this Paillier crypto system is with respect to addition, and this ElGamal is with respect to multiplication of the plain text. And what about this Gold-Wasser-Micali? It is again with respect to addition, and RSA, it was with respect to multiplication. Only one operation in all the cases. Okay, now we are going to see one important scheme which may perform. Let us see whether it perform both operation or not. Okay, that is BGN encryption scheme. This is Bonet Go Nishim. Encryption scheme. We call it as BGN. Okay. Now for BGN, let us first see some of the mathematics on actually this is on pairing, so we have to learn some pairing based. Suppose I'm having two group G1 and G2 be additive group. This is not part of the system, and say GT is a multiplicative group. Okay, say all of prime order P. Now let us take some element. Let P belongs to G1, Q belongs to G2. Okay, be the generator of G1 and G2. Generator of G1 and G2. Okay, how do you define a pairing? A pairing is a map which is defined E G1 cross G2 to GT. Okay, with some conditions. What are the conditions? This is a map satisfying First condition is bilinearity. Bilinearity means for all E comma B belongs to ZP star, this E P raised to A Q raised to B. Sorry, Q raised to again A. Here I am having Q raised to B. It is equal to E of PQ raised to EB. This is bilinearity. Next is non-degeneracy. Non-degeneracy. What is that? That is E of PQ can never be 1. Okay, for practical purposes, E has to commutable in efficient manner. Okay. In the case G1 is equal to G2 equal to G, this is called symmetric. It's called symmetric. And if G is your cyclic, then this is commutative also. This map E is commutative. Okay, that means E of P comma Q, that is equal to E of G raised to say P G raised to Q, which can be written as E of G raised to G comma G raised to PQ. Then I can give it back. I will be having E of Q comma P, as simple as that. Okay, this was all to start with. Now let us start with key generation and all. It was just I was giving you a definition of what is a pairing and how do you doing the pairing based cryptography. Okay, now let us start. Key generation. Okay. Given a security parameter lambda, so security parameter is lambda is given to you, say z plus, generate a tuple. Generate a tuple which is q1, q2, g, g1 and e. This is comma, this is g1 and this e is the map where the q1 and q2 are two large prime. Q1 and q2 are two large prime. Okay. G is the cyclic group. Of order Q1, Q2. Q2, yes. And what is E? E is your pairing map. E is from G cross G to G1. Okay. And let me call N equal to P, Q1, Q2. Let us say. Now pick two random generator G and U from G. And set H is equal to U raised to Q2. Set U raised to that. Okay, then H is a random generator of subgroup. If you observe, this is U raised to Q2. If you put U raised to, this H raised to Q1, it will be a generator of Q1. So H is a random generator of the subgroup G of order Q1. Okay, what is the public key? The public key is capital N, G, G1, your map, small g, and H. And what is secret key? Is your Q1. Only Q1 is the secret key. Okay. How will you encrypt now? Let us see encryption. In the case of encryption, now suppose we are taking binary messages. Suppose M belongs to say 0, 1. It can be anything. To encrypt a message using public key, pick R, a random number R from this set 1 to N, and compute C is equal to G raised to M H raised to R belongs to G. Okay, this is your ciphertext. I'm taking G raised to M H raised to R. I was having G, my message is there, I'm putting H raised to R. How will you decrypt? In the case of decryption, what was your secret key? It was Q1, correct? So you just find C raised to Q1. Find C raised to Q1. What is your C? It is G raised to M H raised to R raised to Q1. Now if you observe, this is going to be G raised to Q1 raised to M. Correct? Because this H was having order Q1, so H raised to R raised to Q1, it will be 1. I'll be having this G raised to Q1 11. Now to recover the message, you have to solve this discrete log. It suffices to compute the discrete log. Of C raised to Q1 to base G raised to Q1. Correct? You'll get your message. Okay, now let us see homomorphic property. Okay, let us quickly show you what is your key generation. Is having two big prime Q1 and Q2. There are two groups G and G1, correct? And this E is the pairing. Picked a random G U from G such that H has order Q1. Okay, now I'm having my public key, I am having my secret key, this is my message. And how do I encrypt? G raised to M H raised to R. Okay, and to decrypt I just have to find C raised to QM, C raised to Q1 raised to M, and then by discrete log we can get the message. Now let us see the homomorphic property. Suppose I am having two messages, say M1 and M2. So I am having two messages M1 and M2. Encrypt it. If you encrypt, what is your C1? It will be say some G1, some G raised to M1 multiplied by H raised to R1, correct? And here your C2 will be G raised to M2 into H raised to R2. Okay, now what about multiplication? First let us see multiplication. Now let us see C equal to C1 into C2. What do you see that? G raised to M1 H raised to R1 multiplied by G raised to M2 H raised to R2 which is equal to g raised to m1 plus m2 and h raised to r1 plus r2. Yes, so this is the encryption of m1 plus m2. Perfect, we got it. Okay, now what about to get what do we get? This is the encryption of addition, m1 plus m2. Now can we get the encryption of multiplication also? Can we get something such that g raised to I'm having m1 into m2 here? Okay, that is the question. I am having addition. Now let us see for can we do something. Okay, not with direct addition. See, because multiplication I got encryption of addition. So can I directly add? Then I won't get directly. See, if you say c1 plus c2, you won't be able to add because this is g1 m raised to m. There is nothing common. Now let us try to do something. Correct? Can I go from some different way? Okay, I'll show you something. Suppose I'm having a g1. Suppose I'm having a g1 which is pairing of g comma g. Okay, and I'm having h1 which is pairing of g comma h. Because I'm having these two, I can always find it. Okay, and what do you observe? This g1 is of order n and h1 is of order q1. q1. Okay, now that means there is some alpha, there exists some alpha belongs to z such that this h is equal to g raised to alpha q2 because it has order n and n is what, q1 into q2. Okay, now let us see. Try to find this c is equal to e in e of c1 comma c2 multiplied by h1 raised to r. Try to see, but observe that this belongs to your g1 because this is even pairing of even c1 comma c2. Now what is your, let us see, what is your c1? It is g raised to m1 h raised to r1 comma g raised to m2 h raised to r2 h1 raised to r. Okay, now if you put the value of h, then this will become e of, this will be g raised to m1 plus alpha q2 r1 to r1. As I told you, here there is a relation. This will be g raised to m2 plus alpha q2 r2 multiplied by this h1 raised, this is h1, here it is h1 multiplied by h1 raised to r. Okay, now what next? So by pairing, I can write it as e of g comma g raised to, it will be product of these two things, m1 plus alpha q2 r1 multiplied by m2 plus alpha q2 r2, and this is multiplied by h1 raised to r1. Okay, now if you solve these two bracket and do this, e raised to e of g comma g raised to m1 m2. Okay, and the other part I can take it like this. Actually, if you solve it, then you'll get to know this will be h1 raised to r plus m1 r2 plus m2 r1 plus some alpha q2 R1, R2. But what do you observe? I got something which is similar to encryption of M1, M2. Correct? So this your C is uniformly descripted. It is encryption of M1, M2, but in G. We got encryption of M1, M2, but in G1, which is a problem. तो G में चाहिए. I wanted in G, correct? So we will not succeed here also. Well, I'll put a box. I'll tell you that this is again fail, because yeah, I of course I am getting encryption of M1 and M2. The thing is that it is in G1. I wanted in G. This is of pairing E of G comma G raised to M and M2, something like that. See, the main goal was to tell this because the fully homomorphic encryption scheme which was given in 2009, it was related to this, actually related to this idea whatever he has given. So that was the main aim to give you this. Okay, then I'll just quickly recall what are the things we have covered today, and then we'll stop. Yeah, so today I start with ElGamal crypto system. We saw the key generation, encryption, decryption, and then we saw that if we add two ciphertext then you won't get anything, but if you multiply then you will get the encryption of multiplication. This is partial homomorphic with respect to multiplication. In the case of Paillier encryption scheme, this is the key generation, this is encryption, this is decryption, and we observe that again if you add two ciphertext then I'm not going to get anything, but if we multiply two ciphertext then I can get the encryption of M1 plus M2. And then next is BGN, which was based on pairing based crypto. So I just gave you the definition of how does pairing work, and then key generation, encryption, decryption, and we observe that if we add two ciphertext, if we multiply two ciphertext, then I'm getting something. I'm getting the encryption of addition M1 plus M2. Now if I add the ciphertext, I won't get anything, but I have some other idea. What I'm doing, I'm finding G1, H1, and I'm trying to see this C equal to E of C1, C2 multiplied by H1 raised to R. And if you observe that at last I'll be having E of G1, G2 raised to M1, M2. But this is the problem because this is E of G comma G. I am getting the encryption of M1 and 2, but this is in G1. I wanted in the group G1, G. Correct? Okay then. Yeah. Okay. Thank you so much, everyone. Bye. See you in the next class.